And the next talk will be given by Noam, and he will talk about verifying equivalence of Spark programs.
Okay, thank you. So this is a joint work with Sarah Cohen, Shahar Yitzhaki, and Muli Segiv. And the main author of this work is actually Shelley Grossman. She's a PhD student, but unfortunately she couldn't come. So I'm here instead of her. But this is actually her work. So let me just give you a one-slide summary of what we do. And I'll do it by basically parsing the title. But to keep things interesting, I'm going to do it from right to left instead of from left to right. So what we are doing, we are verifying the equivalence of a Spark program, Apache Spark. So what is Apache Spark? Apache Spark is essentially MapReduce on steroids. It's a service that sits on a cluster of computers that allows you to process large-scale data by having you send a program to the master, and the master essentially assigns work to many workers, and thus it processes very efficiently. So the interesting thing about Spark is that it allows you to send a program which is written in a general purpose language like Scala, Python, or Java. And once you have programs, you obviously have problems and properties that you want to verify. They can be wrong, you can want to optimize them. And the question that we ask ourselves here is, can we check whether two Spark programs are equivalent? And what do we mean by equivalent? We mean that given the same inputs, they produce the same outputs. We don't care about performance, etc., only about the functional behavior. So what we show in this paper is a verification techniques that allows to verify equivalence of certain classes of Spark programs. Essentially what we do, we reduce the question of program equivalence to a validity of formula and press-program arithmetics, where things become interesting because what the formula encodes is certain inductive argument, which is in a way specific for the class. And the reason that we do it specifically for certain classes of programs is that we show that even for very small, very simple programs, essentially a program that is essentially map and reduce, the problem becomes undecidable. And so what we do, we basically look at different classes of interesting programs, and they are interesting because we looked at real code and tried to extract out of it how people actually program in various levels of success. And we show certain sound and in certain cases also complete techniques for verifying equivalence. And we also provide a prototype implementation which we use to verify certain programs, all the examples that we see in the talks, and what's in the paper. So what is Spark? As I said, Spark is essentially an engine to use cluster programming, to run a program on a cluster. It's comprised of a master node called a driver and multiple worker nodes. Each worker node is giving a partition of the data. And what happens is that the master assigns the work to the different workers, and they compute work locally if they can, and then sends the results to the master, which aggregates them. So the basic data structure in Spark is called an RDD, or resilient data set. We are not going to resilient distributed data set. I'm not going to get into the technical details of how it works and why it's good to use it and how it's overcome failures, etc. But for the purpose of our talk, we can think of basically an RDD as a bag. And specifically in this talk, I will talk only about bags which contain tuples of key and data elements. And essentially, every worker may contain multiple partitions of the same bag or multiple partitions of different bags. So I will call the data bag or RDD interchangeably. But so essentially, from our point of view, the way that we can look at Spark programs is a transformer that gets certain input bags and certain primitive values and produce as an output certain bags and certain primitive values. And in this talk, I'm going to limit myself to programs that take a single bag and produce either a single bag or a single primitive value, although our work is not limited to this case. So let's look at some examples. So let's look at a simple Spark program that tries to basically filter set of tuples, a multi-set of tuples. You can see that although this is called the key, and this is the Spark nomenclature, it's not really a key because the same key can appear twice. So you have, for every key, you have a data. And what we want only the tuples which contain the data which is greater than 50. And we want to then double the data. So the way that Spark works is basically it transforms this bag into an intermediate bag, which the programmer may use directly by assigning it to a local variable in a way, because the interesting thing about Spark is it exposes these RDDs as variables that the programmer can use directly. And then after that, it doubles the data. And you can see that this is very, very similar to a functional notation. What you take the RDD, the input RDD, you apply a filter operator which gets a user-defined function which filters all the data, which filters every tuple if the data is bigger than 50, and then it maps every surviving tuple from this selection into a tuple where the data is doubled. So this is an example for an RDD to RDD transformer. What happens if we want to sum the data, not only to filter it? Then what we do a similar thing. We use an aggregation operation which we call fold, which takes the initial value of the fold and a binary function that sums the intermediate result of the aggregation with the data of the current element. It basically iterates over the bag and applies to every tuple in the bag. So what we get, we first do the filter, then we double the data, and then Spark basically iterates over the tuples, the bag, and computes the result. So, but if we really want to get really fancy, then instead of just computing a single sum, what we might want, we want to be able to compute a sum for each key. This is very similar to aggregate by key or group by key in databases. So the operation is very similar. You basically first filter, then we double, and then the summation is done, but the result is the produced result is an RDD where every key is associated with the sum of the data which was in the original data. Okay? So these are examples for 3 basic operations on RDD. So now let's look at the program and see if they are equivalent or not. So here, let's look at RDD to RDD transformers. So on the left-hand side, what we see a program that first filters the data and then doubles it. And on the other, and here you see a program which first doubles the data and then filters it. Well, obviously, these are not equivalent programs because if you get, for example, this input, then the first program produces an empty RDD, and this one actually produces a one which contains the one element because it's a mapping from 1 to 1 where the data is doubled. If, on the other end, we are looking at programs here which are first filtering the data and then doubling the key, then these operations essentially commute. So in this example, for example, they will filter both elements. If it was given data which is like 80, it would produce one RDD of size 1. And again, these programs are equivalent, and we can prove them. An example for other programs is, for example, if we want to look at a program that first filters, then map, and then does the sum of the data, it's for the same reason this is not equivalent to a program that first map, then filters, and then folds the data, because here it will work on an empty RDD and here not on non-empty RDD. On the other end, if we take write a program where we first filter the data, then we double it, and then we fold it, basically we sum all the data and produce a result, the result is equivalent to if we were looking at a more optimized program where instead of multiplying every element in the data twice, we basically filter the data, make the summation, and then double the results. And we can prove that these programs are equivalent and these ones are not. So this is what we do. And let me tell you a bit of technical details how we do it. So we don't work directly on Spark, because working on Spark basically means verifying equivalence of general purpose programs, like in Scala or in Java, which is not our intention. So we are working on simplified version of a functional language which allows you to use fold by key operations, which we call Spark Lite. The interesting bits about this language is that all the expressions which are used in the program or inside this user-defined function, which are given to the fold or filter or map operations, are given in pressable arithmetic. This allows us to get decidability results. And we slightly extend the pressable arithmetics with tuples and the ability to discuss whether bag is empty or not, but we still show that the resulting is basically decidable because we can reduce it to standard decidability of pressable arithmetics. And what's interesting here is that basically this program turns in this language, every program essentially can be seen as a term. And the reason is that we don't have any loops. We basically have a straight line code a loopless code with possibly if operations. However, we do have implicit loops and implicit nested loops because the fold and the fold by key operations essentially loop over all the data. So what we show is that if we look only at no-AG programs, which are programs which has no fold or fold by key operation, then the question of equivalence is decidable. And the reason is because it's very simple to see that all we need to care about is the equivalence of how the program operates on bags with the single elements. If they reproduce the same results, because the different elements are independent, you can verify this equivalence. And essentially what it translates to into the validity of a quantifier-free formula in possible arithmetics, which is decidable. And we are not actually the first one to make this observation. It was done before. But what's interesting about our work is that we talk also about aggregation. And with aggregation, what we show is that if you have a program which has a single fold operation, which at the end produces a primitive result, then it's impossible to decide if either two programs are equivalent or not in general. And intuitively, it's because we can we can somehow reduce the problem of the halting of two-counter machine into a fold operator, which basically goes over the RDD and operates on it, ignoring the content and basically using the number of elements in the RDD to make the steps. So because this is not, even for such simple programs, the problem is undecidable, we looked at different classes of programs, and I will not go over each one of them, but basically what we show that for different classes we have sound verification techniques, and in certain cases, this is also a complete technique. So let me show you one of these results for completeness, and we are talking here about a class that we call AG1P-Sync. I'm sorry for the very awkward name, but basically what we do, we look at a class of programs which has a semantic restrictions. Actually, the restriction is on the pair of the programs. So each program, basically, what we need to show that if we apply the fold UDF twice, starting from some element, starting from the initial element, then we can get the same result if we were doing it from some element. So essentially, we can jump over to summation and look at it as if it was one, and this restriction is actually, we can verify this property using these three, and once we verify that the pair of programs has satisfied this property, we can show that our verification technique is complete. So this is the flavor of things that we do. So what are the limitations or what we would like to do next? Well, we support only some of the operator in Spark. Basically, we do map, filter, Cartesian product, fold by key. But there are some operators which we find which are tricky. We don't do self-products, not because it's impossible, but because it becomes very technically cumbersome to do all the notations, but this is possible. What's tricky is the handling of union intersection of bags. This is something that Spark supports, but we don't do it because of the bag semantics. Spark, recall, operates on bags, not on sets, and handling intersection and so in union and subtraction with bag semantics is much more complicated than the set semantics. And also for efficiency reason, our implementation doesn't use the complete Cooper algorithm, but uses Z3, although in our implementation we saw that this actually works quite well. So let me finish by a short promo. If you want to see more details, in particular, if you want to see what is the way that the sound technique for verifying the equivalence, where we actually comprise the inductive argument, then you can go see the paper. And also, we report on the implementation, the kind of programs that we verified, and the time that it took, and the kind of programs that we were not able to verify. But if you are really, really interested, then instead you can go and read the technical report, where we also discuss how we handle fold by key operators, which are, again, this is not in general. This also only works for pairs of programs which are specify a certain semantic restriction, which again we can verify using Z3. But essentially, it tells that they preserve the equivalence classes of between keys, the way that they map keys from the inputs to the outputs. So you can find this in the technical report, and that's it for me. So thank you very much. Here is a map of the paper if you're interested. Just to summarize, we handle verification of Spark programs, which are used to analyze large-scale data. We do it by basically looking at certain fragments written in Spark Lite, where we look for the equivalence of program based on input-output relations. And we show that, in general, the verification technique is the verification of equivalence is undecidable, but we have certain interesting classes for which we have sound, and in certain cases, complete techniques, which we implement using Z3 and verified successfully, and in some cases also fail to verify the equivalence of programs. Thank you very much.
So we have time for questions. Yes, please.
I have two questions. The first one is, I guess in most Spark programs, at least the ones I see, the mapper is doing something with strings. Like maybe it's cleaning the data, and then it goes to the reducer, and then it aggregates. So, I mean, I would argue that perhaps the model is too restrictive. Have you thought about how do you parameterize this with a theory, for instance, that the mapper is operating over? The second question is, if you happen to assume set semantics, maybe like there's a distinct call after every operation, what does change in the results? How simpler do they get?
Well, the first question I can answer very easily. We don't really depend on the fact that the things are in Pressburg arithmetic. It was just for the implementation, because we can write code and verify. We have tools that can verify validity using Pressburg arithmetics. But in general, if you have a similar properties of theory over strings, it should work. So it's just a matter of implementation. I don't think that the theory will change. Regarding the second question, is that I think that things will become simpler in the sense that we'll be able to support the operators that we don't support currently, like a union and subtraction, but it might also simplify other aspects of the theory, in the sense that we currently also need to track the cardinality of the element, that it's the same, and we do it using some sort of trick, if you want to call it, and we will not have to do it. But if we can get something more, well, I think we need to ask Shelley, the student who wrote actually did the work. Okay, thank you very much.
Okay. Thank you.